for finals.
Yeah, your finals when? Tomorrow?
I have finals today, I have finals tomorrow, and I have finals Wednesday, then I'm done.
Okay. So what do you want to cover tonight?
I guess I'm going to pretty much go over everything that I've done this year. 1 second.
Okay.
I have some objectives to go over.
Okay.
So I have one that's chapter 1, analyzing the graphs of functions, relations, the continuity and behavior and limits, extrema, parent functions, and transformations.
Probably going to need to send me a picture of that, I'm suspecting.
Okay, yeah.
If there's one thing that is going to be difficult to verbalize, it's going to be that.
Yeah, for sure. One moment.
Okay. You're taking calculus next semester?
Yes.
Okay. I have quite a few pre-calc students that are going to be taking calculus next semester.
Yep. One moment.
And almost all of them have gotten through limits.
This is a pain trying to find it.
Oh, okay. Holler when you've sent it, so I'll know to check.
I'm trying to go through my notes so I can find the paper.
Yeah.
I can find it momentarily.
Okay, because I can search through my database. Unfortunately, I haven't had time yet to go in and categorize everything that's been sent to me in the last month. But I'm sure I have plenty of the problem types that you're talking about.
Yeah, I hope so. Okay, I think I found it, but the
Okay, go ahead, send it. I'd much rather work off of your material than anything I might have gotten from somebody else, because I can never be certain that, you know, the degree of difficulty is the same or even the scope of the coverage is the same.
True. Okay. The only thing is that the answers are on there, but if we cross them out, it'll be okay.
Yeah. Yeah, that's okay. Yeah, just don't look at them as we're going through it.
Okay, sense it.
All right. Number 1. It's the domain of that function.
So, seeing the point.
Why? What's that?
What I'm saying is have to find the points that are furthest to the left and where it ends to the right.
Yeah, exactly. Hold on a moment. Let me blow it up a little bit. So and let me, hold on. All right. In other words, when you're looking at a domain, start there. What's the x-coordinate there?
-4.
Okay. And it's got a parentheses by it because it's open dot. If that was a closed dot, this would have to be a bracket.
Yeah, right.
Okay. And go to the right-hand side. What's the x-coordinate right there?
It stops at 1, 2, 3, 4, 5.
Correct. And notice the difference between this and number 2. Number 2 stops on one end, the right side, but it goes on. When you put the arrow like that, that means it goes to infinity. Okay? So number 1, the domain, you're strictly measuring the change in the x's. Now, to get range, go to the bottommost point. What's the y-coordinate on that?
And the bottommost point is -1.
Hold on, excuse me. I can't hear anything. Hi! All right, go ahead.
-1.
-1, is that what you said?
Yes.
Okay. And then go to the topmost point.
That is 1, 2, 3, 4, 5.
Okay. Do we have values everywhere in between those?
Yes.
Yeah, that's our range. Okay. Now, on the bottom, it's got a bracket at -1. That's correct. It can be -1. We can see that there's a y value there that's -1. And on the top, it can be 5. So that's why there's a bracket there. Okay. For number 2, let's talk about domain. What's the furthest left point?
-infinity.
Always with a parentheses, never with a bracket. And the furthest right point?
Since it's a closed dot, it'll be 6.
Correct. So there's a
With
bracket there. The range, lowest point.
The lowest point is -infinity because of the arrow.
And the highest point.
And the highest point is 1, 2, 3.
Correct.
The bracket.
With
So
the
it's
bracket. Right. All right. Let's move down here. Graph each function using your calculator to find the y-intercept and the zeros. Then find these values algebraically and show all work. All right, hold on a moment. Let me open up both windows here. That's not quite right. What was written right there? It's not x that is equal to 3x plus 4. It's y. And in fact, it's not really fair to say it's y. The only information they've given us is they called it f of x. Well, that's synonymous with y most of the time. It's just a little bit more robust than y. It not only tells us that there's something on the left, but it says it's a function of x. Okay? So, where's the y-intercept?
The y would be at 4.
Yeah, in other words, they've given this to us in mx plus b format. There's the y-intercept always. But more importantly, in fact, I shouldn't even said that, because the y-intercept is where x is equal to what?
Y.
No. When you have a function, okay, and I go through the y-intercept, this point, what's the x value on that point?
0.
Ah, that's the key. Your y-intercept is always where x is equal to 0. So really the way I figure out the y-intercept here is I plug in 0 for x, and that's how I get 4. And the x-intercept is always equal to what?
0.
Where y is equal to 0. So
Yes.
if I want to solve for the x-intercept, I set y equal to 0, and I solve this equation. And you end up getting -4/3 is the x-intercept. Okay. Okay. Number 4. It's the y-intercept.
So x minus 25.
No.
Yeah, x minus 25.
No, the y-intercept is, what do you do with x when you're trying to figure out the y-intercept?
Y needs to be a 0.
Correct. So what's the y-intercept?
0.
No, it's, what is f of 0? That's what the y-intercept is. What is f? What is f when I set x equal to 0?
So then that'll be negative 25.
Yeah, that's the y-intercept. In other words, you set x equal to 0 to figure out the y-intercept. What's the x-intercept? What do I do to figure out the x-intercept?
I solve for x.
I set y equal to 0. It's as simple as that. Don't make it harder than it is. When you're solving for the y-intercept, set x equal to 0. When you're solving for the x-intercept, set y equal to 0. Now, when I say y, I mean either y or f of x, whatever we're looking at. They've told us that this is f of x. So we're not really technically talking about y. We're talking about, though, f of x being 0 gives us the x-intercept. So what is the x-intercept here? How do you solve this equation? In other words, I've set f of x equal to 0. So I've done the first step.
Yeah, x on the opposite side of the numbers.
I didn't quite hear that. Solve this equation?
Yeah, move x to a different side.
No, it's fine where it's at. Solve the equation.
Yes.
So how do you...
So I would do divide, or square root.
Well, you can't take the square root of the right-hand side because it's x squared minus 25. But if I can get that 25 on the other side of the equation, like this,
But add 25.
now you can take the square root of both sides. What do you get when you take the square root of both sides?
X plus 5 and x plus 5.
You get plus or minus 5. You see why?
Yes, because it was
minus 5 squared is 25 also.
True.
Plus 5 squared is 25. And most of my students will leave off this plus or minus, and I guarantee you it's going to cost you points. There's no way you get away with leaving that off if you gave that answer. Now, the better way, perhaps, to find that answer is to factor that. That's difference of perfect squares. How does that factor? You said it.
X plus 5 and x minus 5.
Yeah, x minus 5 times x plus 5. And now when you solve this equation, you set this equal to 0, giving you x equal to 5 as a solution, and you set this equal to 0, giving you x equals minus 5. So there's no chance of making a mistake here. You're going to get the plus or minus properly. Now, this answer that you've given here,
Yes.
I'm questioning the use of the parentheses. In other words, this is the way to give that answer, or this is the way to give that answer. But the way this answer was given almost looks like it's an interval notation, that x can be anywhere between minus 5 and 5. And that's not really true. They're really talking about only 2 points on that curve. And that's where it crosses the x-axis. That's your x-intercepts. And we can clearly see from the drawing that that's the -5 one and that's the +5 one. Okay? But that answer almost makes it look like x can be anywhere between -5 and 5, which is not true.
True.
Let's go down here. And hold on. All right. Even and odd. These are good. Why is that function even? What do we need for a function to be even? How do you tell?
Even number for your root or power?
No, not really. Here's the definition of an even function. F of negative x is equal to f of x. That's what makes an even function. Okay? If f of negative x is equal to negative f of x, it's odd. Okay? Now, let's look at this function we have here. We have f of x equals x squared minus 2. Well, tell me what f of negative x is equal to.
X plus 1 and x minus 1.
No, when you have this notation down there where I've check marked,
Oh, yes.
what you do is you plug in whatever's inside the parentheses, you plug it in for x, wherever you see x. In other words, I go here, and instead of x squared, it's going to be minus x in parentheses squared, minus 2. Well, that's equal to x squared minus 2, which is equal to f of x. Right? So we have f of negative x is equal to f of x. Right there. That's the definition of even, and that's why it's even. And you have to do this test every time. It's not just that we have an even power here, because if I made this the function, is that odd or even? It's not going to be even. It's not going to be odd either. It's neither. But you can't just assume that because we have an even exponent on the x that we have an even function. You have to do this test right here. And if ever they're saying show your work, you really have to do that test. In other words, it's this test that proves whether it's even or odd.
Okay.
Okay. Number 6. F of x equals the square root of x squared plus 3. So tell me what I should write to prove that that's even.
I should
What's the
plug
test?
in y from the x.
The test is to figure out what f of minus x is. That's always the test for whether something is even, odd, or neither. Is you plug in minus x for x. Okay, what is that going to be equal to?
Negative x to the squared plus 3.
Right. Everything's the same, only everywhere I see x, I'm going to put a negative x in parentheses. And you're right, that is the same as what we started with. Which means f of minus x equals f of x. That makes it even. Now, there's something else about even functions. They are symmetrical with the y-axis, as you can see by that drawing. Okay?
Yes.
Odd functions are symmetrical with the origin. That is the sine of x. Is that even, or is that odd, or is that neither?
It's odd.
Correct. That's the sine of x. Now let's look at the cosine of x. Cosine of x, if you draw it on both sides of the axis, that's perfectly symmetrical with the y-axis. That's even. So cosine is even, and what that means is the cosine of negative x is always equal to the cosine of x because it's even. Whereas the sine of negative x, because it's odd, is always equal to negative sine of x. Sine and tangent are both odd. Cosine is even. And of course, if cosine is even, then its reciprocal is also even, the secant. So cosine and secant are the only even trig functions. All the rest are odd. Okay, whether it's continuous at a given point. Let's talk about number 7 because it's classical.
Okay.
Can I simplify this thing? Well, first of all, no, hold on a moment. Is there any problem with x being equal to 5?
I don't believe so.
No, because there's no problem with having a numerator be equal to 0. The only thing we cannot stand is having a denominator equal to 0. So there is a problem with x being equal to negative 5.
Correct.
So right off the get-go, I'm going to say x cannot be equal to negative 5. Okay? But if we look at this function a little bit more and we factor the top, that factors into x minus 5 times x plus 5. And now that x plus 5 in the bottom goes away. But it doesn't really. It leaves a hole. Okay? So this function that now looks like there are no restrictions on the domain still has this restriction right here. You cannot get rid of that restriction just by canceling out and by dividing top and bottom by x plus 5. Okay? So there is still a problem at negative 5, even though the final function that I've circled there just says x minus 5, looks like there's no problem at all. Okay? So if I were to graph x minus 5, that's a straight line like that. Doesn't look like there's any discontinuity, but there is. At minus 5, there's a hole right there. In other words, that original domain restriction stays with the function even though the function now says x minus 5, we can't graph it just like a normal x minus 5 straight line. We have to allow for that hole. And so that hole is, let's see, what kind of discontinuity is that? That's a jump discontinuity, I believe?
I believe so.
You have, here, let me draw some types of discontinuities. If you have a vertical asymptote, and you have something like this going on, well, you have a discontinuity there and here. Those are infinite discontinuities. Okay? So infinite discontinuities are real clear. you pretty much have to have a vertical asymptote to have an infinite discontinuity. I can't think of any other situation where you would have that. A jump discontinuity is where you have something like this. In other words, clearly there's something weird going on there, and I can't draw it without picking up my pencil. So I have a discontinuity, and it's jump, because we have to jump up there and jump back down to draw it. Well, the only thing I'm not sure of is when you have this, which is the situation we're looking at with this number 7, is all we have as a whole. I think it's still called a jump discontinuity. What are your various types of discontinuities? You have infinite, you have jump.
Removable. Jump.
What else?
Removable.
Removable. Ah, that's what this is. This is a removable discontinuity. And it's removable because it would have been a vertical asymptote had the numerator not had an x plus 5 as one of its factors. So it's removable. We don't really have to jump here. We got this whole because we were factoring an x plus 5 out of the top and the bottom. We basically removed an x plus 5. And that's what makes it removable. I can't believe I didn't remember that. But it's not really piecewise. This is a problem I have with my calculus teachers here in Colorado also. They insist upon wanting to call this piecewise. I don't like calling that piecewise at all. I mean, I guess you could, but... All right, I'm looking at number 8. At 2, which function are we using on number 8? Which of the piecewise? This is definitely piecewise. But when x is equal to 2, which one are we talking about? Are we talking about the top one or the bottom one?
I think it's both. You try. Wait, no, if x is equal to 2, then it's automatically infinite, I believe.
It's automatically the bottom one. In other words, you have to start on the right side here. Okay, x being equal to 2 is this function right here. Because whenever x is less than or equal to 2, the function is 16 minus x. Okay, so when x is less than or equal to 2, it's this goes through there with a steep slope, goes through the point 16, a negative, not a steep slope, a -1 slope. So something like that, with this point being 16. And when x is greater than 2, well, the first value we get by plugging in 2. This seems a little counterintuitive, but if I want to figure out how to graph this piecewise function here, then I plug in 2 into the top equation and I get a point of 14. Okay? So immediately I know that I'm going to start out right there at about 14. I have a slope of 5. That is definitely steep. It's like that. So that's the way that function looks. Now, what kind of discontinuity is that?
That's jump.
It's jump. It's not infinite. In other words, all we're doing is jumping. There's no vertical asymptote there. Okay, number 9. What are these letters? Use the graph to determine the intervals on which the hold on. Oh, I get it. Increasing, decreasing, or constant. Now I understand. Okay. Let's look at number 9. Is that function increasing from negative infinity to 2? Increasing means it has to go from lower left to upper right.
Correct.
Slope is always positive of the tangent line. Well, this function goes like this. Okay, it's increasing from here to there. And it's increasing from here to here. But it's decreasing from here to here, and it's decreasing from there to there. So, let's put all the intervals where it's increasing on. Where does it start? Go all the way to negative infinity as your starting spot. So it's definitely increasing from negative infinity to what? What's this x value right there?
1, 2, 3, 4, 5, 6, 7.
-7. And then
I accidentally went by y on here, not the x.
what's that?
It went by y on this instead of the x.
Right. And when you're talking about increasing functions or decreasing, you always are going to be talking about the x. The x coordinates define that, not the y. Okay?
Okay.
The other interval, because there's more than one interval where it's increasing from negative infinity to -7. It's also increasing where? Where else?
From negative 1, 2, 3. Yeah, it looks like about -3 to 1.
Correct. And that's the only place that function is increasing, and you can put it all in one answer in interval notation like this. Now, decreasing. Where's the interval that the function is decreasing?
From -7 to 3.
To -3?
Yes, -3.
And these are always parentheses, never bracket, because at -7, it's neither increasing nor decreasing. And at -3, it's neither increasing nor decreasing. So that's why you always use parentheses there. In combination with what? Where else?
1 to infinity.
I'm sorry, what?
1
to infinity? Yep.
Yeah.
Okay. Number 10. Oh, hold on a second. We didn't actually finish this. Constant, it means it's neither. So there's actually how many points there where it's constant? And where are they?
It's from 1, 2, 3, 4, 5. -5 to 2.
No. Constant means it's neither increasing nor decreasing. That's what constant means. Well, there's only 3 points on this graph where it's neither increasing nor decreasing. There's one of them right there. At -7, it's constant. At x equal -3, it's constant. And at x equal 1, it's constant. Notice something else about those points that I just pointed out. Not only is it constant, but if you took the slope of the tangent line, it would be dead flat, 0.
True.
So when you take calculus, This is an extremely important concept, because if we're wanting to know where on that function we have high points and low points, it's always where that slope of the tangent line is 0. And what does that mean? That means the first derivative is 0. Since that's what first derivative is the slope of the tangent line. Have you gotten into first derivative at all?
No.
Okay. You certainly will next year, but I won't spend too much time talking about first derivative here. But that's why they're asking this question as to where it's increasing, where it's decreasing, or where it's constant. The constant part is almost the most important part, because that's where the function is interesting, is at these points that have a flat slope. That's a local extrema. That's a local minimum. That's a local maximum. That's a local minimum. That's another local maximum. And we're always looking for those when we're looking at functions, is where we have local mins and maxes. Because in the real world, that's what we're trying to solve for, is where is the minimum or maximum of this function occur. All right, number 10. Now on number 10, it's making me question my answer for number 9. I still think my answer is correct. Certainly the increasing and decreasing is correct. And I would say the constant is correct also. It's constant at these 3 points. Okay? Number 10 is a little different, because there actually is an interval from here to here where it's constant. It's neither increasing nor decreasing.
True.
So it's increasing on what interval, number 10?
Negative infinity to 1, 2, 3, 4, 5. Yeah, 5.
5 or negative 5?
Negative 5.
Parentheses or bracket?
I believe parentheses, because we don't use brackets.
Exactly. Always. Correct. And, well, except where it's constant. When it's constant over an interval like this, we do use brackets. In other words, this answer here is correct. -5 with brackets around it, comma to 2, only because of the constants part of it. We don't ever use brackets when we're on an increasing or decreasing interval. And to be honest with you, this is not a typical calculus problem. You will not see this kind of problem when you take calculus, where you have an interval where it's constant like that. It's just, this is an interesting calculus problem because it has all of these local maximums and minimums, whereas this is increasing everywhere except on that one interval where it's constant. So the answer at the top is correct, except this should be a parentheses, not a bracket. The second part where it's increasing. And whether these should be brackets or not, I mean, you can kind of see why this should be a bracket. At -5, it's not increasing, it's not decreasing. So the bracket should apply on this interval for constancy, but never where it's increasing or decreasing are you going to find a bracket.
Okay.
Here we have a question about locate the extrema for the graph. Now, when they say that, here, I'm going to pull this up on my Wolfram Alpha. Sorry to say, I tried to get the virtual TI-84. I couldn't get it installed under Windows 10. I don't know why. So I'll use Wolfram to graph this thing so that we can both look at the graph. Function again is minus x to the fourth. Why are there two plus signs here?
Yeah, I don't know. That's an accident, probably.
Yeah, probably a typo. So minus x to the fourth plus 2x. Let's graph that. Minus x to the fourth plus 2x. Minus x to the fourth plus 2x. The thing I love about Wolfram Alpha is it tells you what you put in. And I put it in properly. Okay. So we've done the first part of their request, which was we graphed it. And now let's figure out where local mins or maxes are. What do we have in this graph? We have an extrema. What is it? Is it a local minimum or a local maximum?
I believe the extreme is minimum.
It's a maximum. In other words, there is the maximum value that y can take on. Where does it occur? Somewhere along there on the x-axis. If we zoom out a little bit, it looks like that occurs at 1. I can't quite tell on this. But on your calculator, you could put your trace on there and figure it out. And that's what they want you to do. In other words, you can't really tell by looking at the graph where that maximum occurs. If I look up here, it's not at 1. It's closer to about 0.7 or 0.8. But again, they want the x value that thing occurs, and not only that, but what is the y value at that x value. So they do kind of want both the x and the y coordinates of this point. But the real one they're asking about is the x coordinate. Where on the x-axis do we have a local extrema here? And not only is that local, but that's absolute. That's an absolute maximum for the function right there. You know, left and right, it goes down. So there's no place on the function that's higher than that.
True.
And it's not that easy to tell, but notice that if I had calculus, I could take the first derivative of this function, set it equal to 0, and find out exactly where that point is. And that's
I see.
That's the beauty of calculus, is it allows us to find out. I can't even tell exactly where that point is from this graph. It's not accurate enough. It's not detailed enough. But I could find out what that value is by taking the first derivative of that, setting it equal to 0, and I get minus 4x cubed equals minus 2, so x cubed equals 2. So the cube root of 2, no, that doesn't sound right. But anyway, let's go back and look at your other functions here. And it did look a little like this. Did you draw these curves on here?
No, my friend didn't.
Okay, but I mean, somebody graphed it in the calculator and then pretty much copied what you were looking at onto the paper?
Correct.
And you put the trace on there, and it looks like the x value occurs at 0.8. Now, it does say round to the nearest hundredth. So you need another figure in there. It looks, unless it was 0.80, but even if it was 0.80, you should put in the 0, because otherwise we don't know that it's a 0. Did you make a mistake and round it to the nearest tenth, or was it really 0.80?
I'm going to check that right.
Yeah, that's what you really, that's the purpose why you would put the 0 in there, is to let us know that you've rounded it off to the nearest hundredth place. And the y value is 1.19 or 1.14, I can't tell from the writing.
19.
19, okay, and that looks like it was rounded off to the nearest hundredth, I guess. I mean, I can't really tell without seeing all three places, but you obviously know how to do that. Put the trace on there and figure out where that maximum is?
Yes.
Okay. In fact, it's not just putting a trace. You have to put a line to the left of it and another vertical line to the right of it, right? And then it tells you what that point is right there. Okay, over here, number 12, that certainly looks like the graph. It's got a y-intercept at -3, and it's a basic parabola with a vertical stretch factor of 3. Okay, so if we want the minimum on this, we know it's right there on the y-axis. And the coordinates on that are 0, -3. And we know that merely because we know what a parabola looks like, and that's a parabola that's been shifted down by 3 units. So we know that its vertex is on the x-axis, or excuse me, on the y-axis. And we know it opens up, so it has to be a minimum, not a maximum.
Oh yeah, the reason why it's a 0.8 is because it's originally 0.793, and then you have to round it to the nearest hundredth.
That rounds to 0.79 then.
True.
If it's 0.793, then it rounds to 0.7.
Yeah.
Okay. Now let's say it was 0.798. Well, now that does round to 0.8, and 0.8 is as accurate as 0.80, but when you put the 0 on there, it tells everybody that you've rounded it to the hundredths place. If you leave the 0 off, it looks like we rounded it to the tenths place. And in fact, that's what you did do, was round it to the tenths place. So that should be 0.79. Oh, okay, here's all about the transformations. This is good stuff to go over because I noticed that there were a few difficulties on this topic last time we went over it. So number 13, what is this function doing to the parent function? If that's the parent function, what's happened to this function? There's 3 things that have happened. One of them is this 1/2, one of them is this -2, and one of them is this +6. Tell me what each one does. What's the 1/2 do?
It compresses it vertically because it's less than 1.
Good. What's the -2 do?
It moves it to the right 2. It translates it to the right by 2.
Horizontally, correct. And what's the +6 do?
It moves it up 6 points.
Okay. How come all the answers are on here?
Oh, it's because I have to rewrite it into the formula. I have to like show the equation for it.
Ah, so this is the answer. Oh, yes. I see. They're telling you, I get it now. They're telling you all the transformations and they need the equation of it. Okay, I got it.
Right.
So number 14, we are reflecting over the x-axis.
So I need a negative.
In front of the absolute value sign. We are shifting up we're shifting 2 units to the left, so you need a plus 2 inside the absolute value. And you're shifting 1 unit up, so you need a plus 1 outside the function. So what you've written here is correct with the negative sign in front of the absolute value.
Okay. So you have a negative.
If you ever have any questions as to that, whether you've done it right or not, plug in a point. In other words, here, let me show you what I mean. If I said I hate Windows 10 yet this session?
Yes.
Only once? Let me say it again.
Yeah, only one.
Let me say it again. All right. So here, I'm going to start out drawing the parent function. Slope of -1 there, slope of +1 there. That's y equals absolute value of x. Okay? They've told us to reflect over the x-axis, and you always do your reflections first. So that's the first thing I would do. And then shift it 2 units left. That's the next thing I'm going to do. And finally move it, what, up 1 unit?
Yes. So I'd have to have a plus 1 on that side.
Well, that's your curve. In other words, I did everything that they said. Okay? Now, let's check our function that you came up with. You came up with y equals negative x plus 2 plus 1, correct?
Yes.
Does this curve reflect that? Well, pick a point on the x-axis and see if that's at -2, right?
Mm-hmm.
So plug in -2 and see if you get +1.
Okay.
And you do.
So plug in -2, yeah, you do. Correct.
Okay. So this curve matches this function. And that's not a bad check if you have the time to always kind of do that. Although with these questions here where they're giving you the transformation and want you to come up with the function, you may not need to do that last test. It doesn't seem to be as critical. Certainly if they give you the function and say graph it, that's a great final step, is to plug in a point and make sure that it comes out where it's supposed to. Number 15. First, reflect over the x-axis. Always do those reflections first. So what am I missing in your formula here? Reflection over the x-axis always requires what? A negative.
A negative.
A negative in front of the function.
The equation.
Not in front of the x, but in front of the function. So I'm going to get a negative sign right there.
Correct.
And we're going to do them in order. Vertically expanded by a factor of 7. What am I doing wrong here? How come this description applies to 15, correct?
Mm-hmm.
I think you've got them backwards here. You got the -7 on number 16. This vertically expanded by 7 after the reflection applies to 15. There's your parent function on 15. So we're going to reflect over the x-axis. We're going to vertically stretch it by a factor of 7. So what's our function look like? Our function started out looking like this. Hold on, I hate this blue. Our function started out looking like this. Well, the first thing we're going to do is reflect it. So now it looks like that. Next thing we're going to do is vertically expand it by a factor of 7. I like to do each of these steps separately so I can see exactly what's going on. And finally, shifted it 4 units to the left. Well, that's a horizontal shift, so it's got to go inside the function. Like that. So what it looks like you did was come up with this based on a parent function of x squared. They wanted you to come up with this based on a parent function of x cubed. The x squared function has different things going on. In other words, you applied their description from 15 to the function in 16. You see that?
Yeah.
Okay. So let's do 16 since I'm not looking at it, but it's a good one to do because we're not looking at the answer. If the parent function is x squared, let's take the first thing they say. Horizontally shifted 5 units to the left. So what's that step going to be?
It'll be inside the parentheses of 5. So would it be 5x squared?
It'd be x plus 5. It's quantity squared.
Okay.
Okay. I'm tempted to avoid this, but not really. To me, you don't really understand transformations unless you understand how it looks in f of x notation. Okay? Well, if I call this f of x instead of y, there's the parent function. Well, what is this down here? This is f of x plus 5. That's what it is. And now, by looking at that, that tells me I have a horizontal shift that's happened. You get it?
Yes.
In other words, being able to look at this and figure out that we're looking at f of x plus 5. And since we're looking at f of x plus 5, this means horizontal shift. If I was talking a vertical shift, I would write it this way.
On the outside of the function.
Exactly. This would be a vertical shift of the function, and it would look different also. It would look like this. And notice that that's exactly what that is. F of x plus 5 is x squared plus 5. So all I've done is add 5 to both sides. In fact, you could look at it like that.
Okay.
Okay. So the first thing was the shift. Hold on. Okay, so your answer here for 16 should be what?
Plus 5 instead of that.
Yeah, exactly. In other words, x plus 5 quantity squared plus 6. Okay.
Well, I appreciate it.
Oh, sorry, I didn't notice the time. Yeah. Yeah. Good luck, Taylor, if you have your final tomorrow.
Thank you.
You're welcome. Talk to you next time.
Okay, sounds good. Have a good night. Bye.